Kia ora, good evening, welcome. My name is Alexander Gillespie. I am a Professor of Law and the Pro-Vice-Chancellor of Research at this university, the University of Waikato. I'd like to welcome you here tonight to Warwick Holmes' lecture, and I've had the pleasure of speaking to Warwick for the last 15 minutes, and I've had an idea of the insights about what this lecture is going to be about. There's many things to mention, in particular about a man who was very humble and stresses that he was not brilliant at school, but it was through hard work and diligence. But the link I must draw out at this point is not just the diligence and the hard work, it's also the scholars that he learnt from, and in particular, one of our own professors, Jonathan Scott. Would you please stand so the audience can see you? Thank you. The work that has made Warwick very famous of late, especially in the media, he's been almost trying to trump the Prime Minister on the ponytail story. Good luck with that. It has been with his work with the European Space Agency, and in particular the Rosetta spacecraft, which is making a new understanding not just around Mars and the asteroids, but actually landing on a comet. And as was explained to me before, this will change our way, the journey, not just of small parts of space, but the entire way that we see the solar system. I've been told to emphasize that the importance of what Warwick does in terms of his scholarship and his contribution of over 29 years in the agency is in terms of science and space exploration. But my view of his work is somewhat different in the sense that I come at matters as a lawyer and someone with an interest in history and humanity, and I see the work that has been carried out by people like Warwick Holmes is changing the way that we see ourselves as a species. It takes not just reason and science, it takes a question of identity, and to me it's the vision of what the future of cooperation looks like. Ladies and gentlemen, Mr. Warwick Holmes.
Well, good evening to you all, and welcome to Waikato University. Tonight, I'm going to be explaining to you the story of the Rosetta spacecraft and its orbiting and landing on the comet 67P, and I'll explain that naming to you later. But I'm going to start first of all with a video that was made by a Discovery Channel documentary, just showing the excitement in the control room in Darmstadt in Germany at the moment, just a few moments after the Philae lander probe successfully touched down on the comet. So I'll just play this for you for a few minutes, and then I'll start the lecture.
This is it. You are watching history being made. The first ever landing on a comet. I'm Dan Riskin. I am in the most exciting place on the planet right now, the European Space Agency in Darmstadt, Germany. And this crowd is cheering because an incredible group of scientists just put a lander on the surface of a moving comet. Now, they made it look easy, but this mission and what it's about to do are groundbreaking.
Is it real? Are we there?
This is a big step for human civilization.
It could revolutionize everything. Desperate to reveal life's origins.
They're a treasure chest with a view back in time.
A quest decades in the making.
It's one of the most difficult things you can try.
An epic adventure to chase down a dragon and ride on its back.
Cherry on the top is really the landing.
Touching down,
it's all down to Isaac Newton now.
Where no one has landed before.
We're moving in for the kiss.
But first, separation anxiety. 7 agonizing hours.
I don't have any fingernails, they're gone already.
We are on the Comet.
A comet, up close with unprecedented clarity.
We're making history here.
This is one for the record books.
We know the world is watching this mission.
Okay, so you can see it was a very dramatic event. So I'm going to explain how we did all that. So tonight I'm going to be presenting, I hope, answers to these fundamental questions. What is a comet and why visit one? How we built and test Rosetta in the Philae lander. The launch and the mission highlights to get there. Comet 67P, the images we took when we were there, and the landing of the Philae probe onto the surface. So what is a comet and why do you want to visit one? Well, the big difference with a comet is that it is a planetary body of our solar system. It's gravitationally bound to the sun. But it's extremely different than all other planetary bodies which have been visited by all other missions during space exploration. And that includes all the planets and even the sun itself. The planets and the sun have been heated by the process of gravitational collapse and by obviously the fusion of the nuclear reaction of the sun. Comets were the original primordial material that first formed when the solar system was forming 4.5 billion years ago. And it was the material that was slowly condensing and collapsing under gravity before the sun and the planets existed. So there was no light, there was very little gravity, and it was just this process of elements slowly coming together and making molecules we've never seen before. The best analogy I can give, it's like burning a piece of paper and never seeing the white piece of paper. So the terrestrial planets we live on and the sun have all been burnt. So that chemistry has been completely changed by heat. As of this mission, we have never seen a white piece of paper. And that's what this mission is all about, is trying to understand the chemistry of the white piece of paper, the cake mix of our solar system, and trying to visit and land on there to find out what chemistry, what physical processes, what makes a comet. Now, I've got 100 slides tonight, and I have to go through them fairly quickly, so I want to try to give as much information as I can. Afterwards, you can come back and ask questions at the end of the presentation. So this is an image of the early solar system, and the cometary material is here on the outermost extent. Now, this picture is a bit misleading because you can see we have a sun, and we have some planets that have already formed. But if there wasn't a sun, there'd be no light, and there'd be no image. So this is trying to show how cold and dark and miserable the solar system was when comets were made 4.5 billion years ago. So the fundamental question is, how do we get from this ball of dust, which is from a supernova explosion, another star which has already exploded, generated lots of dust and new elements, whizzing through space and collapsing to form a new star, a new solar system? How do we get from that gas and dust to planet Earth with water to intelligent human life here at Waikato University? Every single one of you is made of cometary dust from the elements of a supernova explosion more than 4.5 billion years ago. How did we all get here? How can we make a spacecraft to go back and land on the comet? So this is a video just briefly showing the process of the cometary bombardment during the formation of the Earth, when it was still a red-hot molten ball of magma. This is before any of the oceans formed, and the planet was still cooling down, and then there was a secondary bombardment phase which brought what we believe, the water for the oceans, and the primordial chemistry to start the evolution of human life, of all life. So we had a tantalizing glimpse of what a comet was like when this meteorite came in and hit Australia, called the Murchison meteorite. And inside this meteorite, they realised that there was something very strange, because when it hit this town of Murchison, which is in Victoria, in Australia, the residents of the town saw it come in. There was this enormous bang as it went at a sonic speed through the atmosphere. But there was a smell that was left behind, a smell of bitumen and wet hay was the best way that they could describe it. They thought, well, that's very strange. What on earth is that? They analysed the chemistry of this rock, and found more than 100 amino acids in this rock from the outer extent of our solar system, because they realised that this was in fact an evaporated core of a comet. There are only 20 amino acids on planet Earth and in all of our bodies. So there's an extra 80 amino acids in this rock from space, which we've never seen before. We know what the chemistry of them looks like. We can make them in a lab, but they do not occur naturally on Earth. So we realised immediately something very, very strange was going on with comets, and we wanted to go out there and find out what it was. So inside this piece of Murchison, they did some very advanced chemistry, and they found what they call nucleotides. And this is the bonding molecules which are used for helping to connect the RNA and DNA chains together. And this was very exotic chemistry that we found just on what we thought was an inert rock from deep space. It's anything but. It brought with it the fundamental chemistry that helped kick-start life. It didn't have life itself. It was too cold and too small and in a hard vacuum. But it had the building blocks, the Lego blocks, to help make life very quickly. So how do we get out to a comet? Now, the problem is comets are moving very fast, and they're very far from the sun. So we had to catch the comet which we planned the mission for, we had to get an extra 50,000 kilometres an hour of speed. And the largest rocket we have, and all the fuel in the spacecraft, was only going to get 8,800 kilometres of extra speed to catch the comet, which is nowhere near enough. So we had to design a mission that used what we call gravity assist, and that is we fly around the sun and we synchronize with planets to get the gravity of those planets to pull us forward, a bit like a skateboarder grabbing the back of a bicycle to get an acceleration to go down the road. But we have to wait for the right bicycle to come past, going in the right direction, to grab it, to go in the right direction. So this was the, whoops, I'm sorry. I missed the video. Okay, so this video shows that process of planetary gravity assist of the 12 years to get the spacecraft out to catch the comet. Okay, so this is the launch on the 2nd of March 2004, 11 years ago, more than 11 years ago. The white line is the spacecraft. We left the Earth, but we came around and we synchronized with it again to get the velocity of the Earth to accelerate us forward by 15,000 kilometers an hour. We went out a bit further then because of that extra boost in speed. We came back in, and this time we synchronized with Mars here on the 25th of February 2007. And this changed our direction again to come and hit the Earth, well, not hit the Earth, get the gravity assist of the Earth. And we had another very large acceleration, another 15,000 kilometers an hour. Each time, the circles are getting larger and larger. We went past asteroid Steins through the asteroid belt. As we went through, we just have a look. We saw an asteroid we chose. Back in for a third gravity assist. This whole sequence of gravity assists took more than 10 years to finally get the speed to get out to the comet. We found another asteroid, Leticia, which I'll show you images of. This is the comet out here. The problem is, we then had to go into hibernation because we're getting so far from the sun, the solar panels could not generate enough electricity to keep the spacecraft alive. And we had to put it into hibernation, I'll explain that as well. Then we turn it back on again, 20th of January this year, last year. And then we follow the comet for 8 months until we do our first orbit around the comet in the 6th of August 2014. And then we're mapping the surface and we're starting our very intensive science phase during that period. The comet slowly becomes active here, and we put the lander down before it gets too active. And that was on the 12th of November. And then we're about at this point here, at the moment. We go past the closest point to the sun called the perihelion on the 13th of August 2015. And the mission ends roughly past December in about July of next year. So that shows you the complex trajectory that we had to do to actually catch the comet and to get this enormous speed. This is what the spacecraft looks like. It's Rosetta. This is I'll call it like the mothership. It weighs 3 tons. It's got 64 square meters of very, very efficient, very expensive solar panels to generate the electricity far from Earth. This is another view showing the Philae lander, which weighs about 100 kilos. So the spacecraft weighs 3 tons when we first launched it, 1.7 tons of which was fuel only. 100 kilograms for the lander, bolted on the side, which we then deploy to put down onto the surface. This is just showing a summary of the 11 instruments, extremely sophisticated instruments. If we're going to go all that way, we're going to take the best instruments we can. We've got atomic force microscopes, mass spectrometers, gas chromatographs, RF tomography, every ology, oscopy, ionometry you can imagine. If we're going to go all that way, we're going to make it count, okay? There are hospitals, city hospitals, which would be jealous of the instruments this spacecraft has got. So this is the lander, Philae, free flying. So it's got, again, 10 instruments on board Philae, together with its landing gear deployed. I won't spend too much time on that because we're running out of time. So these are the instruments again, as well. Again, mass spectrometers, gas chromatography, RF tomography, everything you can imagine. We've even here in the feet got microphones and sounding speakers for pinging, like sonar peeps, into the sound, into the body of the comet. And it's like sonar seismology, is what I'm trying to think of. So this is my role on some photos of me just working on the spacecraft. This is I started 15 years ago, in the year 2000, worked on it for 4.5 years. I was actually involved in testing, in principle, most of the software on the spacecraft. So I was doing the building, the testing, and then the launch up until 2004. So these are different just photos in different phases during building and testing the spacecraft. And went down to French Guiana in the top end of South America, which is where the European Space Agency launches most of its missions. And we had a dedicated Ariane 5 just for our launch because we were going in such a strange direction. This is some views inside the spacecraft. So we've got here these laser gyroscopes. These are called reaction wheels, which are used for moving the spacecraft, and an enormous amount of pipework involved with the 24 little thruster engines we use for moving the spacecraft around in space. When we were building the spacecraft, we had to test it in a representative environment to be sure that the spacecraft would survive the rigors of deep space. And the thing to notice here, this is in a 2,000 cubic meter vacuum chamber. We pump all the air out. In the walls here, we flood them with liquid nitrogen to get it down to minus 200 degrees Celsius. And we actually then have to test the spacecraft over a range of more than 300 degrees Celsius. So imagine you've got a TV set, you put it in the fridge and it works in the freezer, you're thinking, okay, that's all right. Well, then put it in the oven at 300 degrees and see if it works. This is what Rosetta had to endure for 10 years. There's an enormous temperature range as it's going towards the sun and then further away. This is a view of the lander on a vibration table. This is where we shake all the components of the orbiter and the lander to enormous vibration levels to survive the rigors of the launch of the rocket. Even though we then drift for 10 years in 0G, which is the most benign environment you can imagine, the launch is absolutely horrendous. So we've got to design it to survive the launch. This is a view inside the lander, and you can see it's probably the most complex box of electronics certainly I've ever seen. It was just a seething mass of electronics. Circuits, computers, gas chromatography here, these little bottles here are full of helium for using for our gas chromatography experiments. This is so we're getting up to the launch now. So this is the launch site in French Guiana. This is the Ariane 5 being wheeled out to the launch pad here. And on 2nd of March 2004, we were launched off to start the mission. This is the operations center in Darmstadt in Germany. This is the epicenter where all the control of the spacecraft is done, but with signals sent via antennas, in this case in Australia. There were 3 antennas we use, and this one, there was the first one that was built in 2002, and it's 36 metre diameter, and it was the only one for 8 years. So for the first 8 years, getting out towards the furthest extent, only this station existed, and then 2 more were built in Argentina and in Madrid in Spain. But this is a little bit like the Dish movie for Apollo 11. We've got our own little Dish story now with this one in Western Australia that helped Rosetta to land on the Comet. So we've started the mission, and this is one of the flybys. It's just an image showing what we think the spacecraft looked like as it flew past Mars. But this is a real image from Philae, the lander. As we flew past any planetary bodies, we turned on all the instruments we could to test them, to be sure that they were working before we got out to the Comet. And this is a little selfie we took with Philae looking over the shoulder of the back of the solar panel from Rosetta and looking down onto the moon just 250 kilometres below us, travelling at 26,000 kilometres an hour. As we flew past, we took some images of Mars, and with different filters we use. We have 17 different coloured filters, and we exercised all of them, and this tells us what the components of the chemistry of the atmosphere of Mars are, for example, which one day we'll be doing the same thing when we get to the Comet. So then we carried on. We went past asteroid Steins for a flyby, and I hope this is going to work. Okay, so as we're flying past, this is 800 kilometres from the asteroid, which is the distance from Sydney to Melbourne. Sorry, I don't know the New Zealand equivalent of that, but 31,000 kilometres an hour, and it's only 6 kilometres across. So we've got very powerful cameras to zoom in and get these images as we were flying through the asteroid belt to, again, exercise some of our instruments for when we got to the Comet. Then later on, we went past another asteroid. This is again going through the asteroid belt. Sorry, missed that. And this is a much larger asteroid. This is the second largest asteroid of the asteroid belt, 100 kilometres across, but this time we were 3,000 kilometres away and travelling at 56,000 kilometres an hour. So these are very fleeting, very fast flybys, but we still did everything we could. And that was the best image we got from Leticia. Then came the hibernation, and this is when we had to turn the spacecraft off for 2.5 years. We set 4 timers on board to 80 million seconds. And all 4 of them were counting down to 0. Any 2 of which got to 0 would wake the spacecraft back up again. So as we were going out to the furthest point, we had to turn the spacecraft off because we didn't have enough electrical power, except to keep the timers running. And that meant turning off the receivers. So even in an emergency, we couldn't wake the spacecraft up. And this is the first time ever this has been done in a deep space mission, because if we couldn't turn it back on again, that's the end of a $2 billion project. So we waited nervously for the wake-up call 2.5 years after we turned it off, and we had to point the antennas to the equivalent of that black dot on the full moon, so the half moon. So if you see, everyone's familiar with the moon, that's how accurate we had to point 2 great big 70-metre antennas to actually pick up this signal if it was going to come anyway. So that's how accurate our pointing had to be. And these were the 2 signals we were looking for. This is one dish in Canberra, a 70-metre NASA dish, and another 70-metre dish in Goldstone in California. And luckily, the signal came. Now this is the details of the orbit of the comet we're trying to catch. This is Comet 67P, the 67th periodic comet. The periodic comet is one which has been captured by Jupiter and into a closed orbit, a much smaller orbit, which means that we actually have a chance of catching it. So when we came out of hibernation, we were out here in January 2014. It took us 8 months to catch up to the comet to do our first closed orbit. And that's when the really intensive science phase began. And so then we did the landing here on the 12th of November, 2014, and today we're at about this arrow here, as we're just about to enter the highest activity phase of the comet, which is when it starts to evaporate and all these volatile chemistry starts getting blasted off the surface. So we did a science phase here where the comet is dormant, and we looked at the dormant chemistry, and then we're doing another phase here where we look at the active chemistry. The whole time, the orbiter is following the spacecraft right through to about July 2016, when we run out of fuel, chemical fuel, and then we will land the orbiter onto the comet as well to meet its little lander as well, the orbiter and the lander on the comet together. So today, this is where we are, looking down on the solar system. So this is the orbit of Jupiter out here. Here is Mars and Earth. And we're outside the orbit of Mars at the moment, travelling at 92,000 kilometres an hour, 387 million kilometres from Earth, 270 million from the Sun, and it takes 21.5 minutes for images from the comet to get to Earth travelling at the speed of light. 21.5 minutes to wait for the speed of light. We've travelled a total of 6.9 billion kilometres, almost 7 billion kilometres, going 4 times around the Sun, doing the gravity assists to catch the comet to get to this point today. Now, these are the first images we had as we were approaching the comet. This is 1 million kilometres away, and this is our navigation camera that we use for knowing which way we have to go. So this is a real-time display of the navigation camera. Can anybody see the comet in that image? Okay, well, just above the red dot, one of those stars is stationary. I don't know if you can see it. It's right above the red dot. That is the comet. So luckily, we were pointing in the right direction. And that shows you how difficult the navigation is to try and catch the stars to see where we're going. Okay, so these were the first images of the comet as we were coming in. This is in August of last year. And there's a sequence of still images we've strung together to make it like a movie. And then we realized that something very, very, very strange was going on. We were not expecting to see this. The shape is extremely unusual. It looks like 2 comets which are joined together. It's a head and a body that seem to be stuck together with a neck region. So somebody, of course, made the astute observation, well, it looks like a rubber duck. Well, it does. Tell me that's not a rubber duck. 10 years in orbit to find a duck, okay? So then we went into orbit and we started a very intensive imaging campaign where we were looking for all these new features we've never seen before on a comet. This was the first comet that anyone has ever gone into an orbit around or got this close to. So one thing I have to emphasize is that this image shows a nice bright white comet, okay? Well, in reality, the surface of this comet is blacker than coal dust. It's like the toner cartridge powder you get in a photocopier. We've got extremely powerful and very, very sensitive cameras which can enhance the brightness and the contrast to actually see this thing. Only 6% of the light reflects off the surface of this comet. We're at a distance where the solar power is at 1/10 of the brightness we have here at Earth, so only 0.6% of the light actually comes off the comet, which is absolutely invisible. If it was standing right here beside us, we wouldn't see it. It'd be just a black nothing. So these images are truly incredible. What we've done here is we've even enhanced using the filters, the coloured filters, to find out what the true colour looks like. Again, we're having to enhance it to even show it to you, but this is what the true colour of a comet looks like. And then we were flying around, and just every feature, every image we took, we found features and unusual things we've never seen before. So here again is another selfie by Philae looking over the shoulder of Rosetta, solar panel. This is the back of the solar panel with the comet in the foreground, with a few gas jets coming off. And we started, the important thing to realise too, not only is the surface of this is jet black, blacker than coal dust, everything you're looking at does not exist on Earth. These are not boulders, they're frozen chunks of ice which are gases. It's frozen carbon dioxide, frozen carbon monoxide, frozen nitrous oxide, frozen methane. These are not boulders. It's frozen chunks of gaseous ice, together with maybe amino acids. We haven't found that out yet, we're still looking. So there's a lot of carbon chemistry, a lot of polyaromatic hydrocarbons, they call it. It's like soot, sooty chemistry, and frozen gases. Even though it looks like a hard surface, or it looks like it could be somewhere in Switzerland, it certainly isn't. None of this surface, none of this chemistry corresponds to anything on planet Earth. So these are, again, I'm just giving you a series of images to show you the surface features and the unusual surface features, I should say. And everywhere we looked, we were seeing unusual things. There's a very rough surface. You can see it's very old. There's been a lot of aging on this poor old comet. It's 4.5 billion years old, and yes, indeed, it is old. So then we had to start looking, I'll just show you this here. This is where we have some craters. Now, these are not impact craters or volcanic craters, certainly not volcanic, it's way too cold. These are where basically gas and volatile components inside the comet have evaporated and they come through and they form these like evaporation volcanoes, I guess we could call them. So we put many thousands of images together to make a simulated fly around the comet. So this is about 20,000 images have been stitched together to make a virtual model of the comet. And we use this then for planning our navigation and our science of what we want to see. And this is the power of the computing that we can do today to actually do this kind of imagery. So then we started looking very carefully to try and understand, well, look, what are some of these strange features? Well, one thing we noticed were these large cylindrical holes that looked like a well that had been dug straight down into the comet. I think it's strange, what on earth is that? So then we did a bit more image processing, and we found out that here in the middle, you can see there is some venting going on. And we realized that these were basically vent holes, where the volatile chemistry inside the comet, when it gets close to the sun, it blasts out like a fire hose. So these were the active sites where the venting that creates the tail of a comet seems to be coming from. And again, we see another vent hole, this time with this sort of oozing remnant, which is basically, it's a molten gas, which came out as a gas at one moment. It then solidified into a liquid, and then it froze solid again. So this is like liquefied, solidified nitrous oxide, for example, which you'd only ever see on a comet with a temperature at about minus 90 degrees, which is the surface temperature which we can see today. Inside the comet, it's minus 190 to minus 240 degrees. Extremely cold inside, a bit warmer on the outside. Looking sideways into one of these wells, I can't think of a better name, we noticed there are what we call goosebumps on the side. Looks like lots of little golf balls on the surface. And this seems to be one of the theories of how comets formed. They're formed by lots of little golf balls sticking together. And there's another theory, which is an aggregated layer theory. But we saw both, in fact. So both theories are in fact correct. This is the layered theory, by the way. So these are the layers, and we had the golf balls in the previous photo. So now we're getting into some of the science results, and I have to cut this short because I'm running a bit out of time. But first thing we discovered is the comet is very light. It has half the density of water, so if the comet was on the sea, it would float. This is a thermal map showing the temperatures, so we've got minus 40 to minus 70 as we're approaching closer to the sun, but minus 110 to minus 240 inside again. So this is a thermal image map taken by infrared spectroscopy of the comet as it was rotating underneath us. We collected some dust particles out using the orbiter. This is not on the surface yet. Dust is being blown off, and we could catch those. And then we analysed the dust particles. So even if we didn't get onto the surface, we could still analyse the material of the comet. And we blast this with an Indian beam, and we can get a spectrum showing what materials there are. Sodium, magnesium, and all the what we call refractory elements that go into making the comet. And here we have the gas chromatography. This is showing the gases we found. So there's oxygen, methane, water vapour, carbon monoxide, carbon dioxide. And then we do some mass spectroscopy. And this is where some of the best instruments we have are used. And this is where we try to measure molecules or the elements by their mass. Okay, so we've got here the mass of carbon monoxide has 28 atomic mass units, we call it. But so does nitrogen, and so does silicon. But because of the spectral resolution, we can split the mass of these common massed elements and molecules with enough resolution to actually identify the separate components of the separate chemistry, even though they have almost the same atomic mass. And this is an incredible instrument to get working 500 million kilometres away from Earth to do this kind of measurement. And what did we find? Well, we found a lot of smelly, disgusting chemicals. And we had acetylene, alcohol, ammonia, amino acids, hydrogen sulfide, methane, formaldehyde. Every single one of these smells disgusting. And that's unfortunately the truth of the comet. We're made of the water and the carbon chemistry that made us all. It's not like, they say in the nursery rhyme, girls are made of sugar and spice and everything nice. Well, it's not true. We're made of smelly comets, okay? So this is just to show how dark the comet is in relation to the imaging I was telling you before. So if we were 1 million kilometres away from these four bodies in space, Enceladus is one of the moons of Saturn, and Earth, of course we're very familiar with, and the moon. This is the relative brightness of a camera 1 million kilometres away taking a photo, and of the comet 67p from the same distance. But that picture is 100 times brighter. And you can see, we can still barely see it here. I don't know if you can see it, yeah. That's actually, I've had to magnify that 100 times in brightness to even see it. So just trying to give you an idea of just how dark and how small. It's only 4 kilometres long, 3 kilometres high, and 2 kilometres wide. I forgot to mention that. It's a very, very, very small object. It's very dark, and it has no gravity. It has gravity, it has 100,000th of the gravity we have here on Earth. So everything about this object is small and difficult to find. So we've been in orbit, and we then started measuring what we call the plasma field. The plasma field is where the evaporated material coming off the comet gets ionised by the sun, and it gets modulated by the solar wind. I won't go into the physics of that, but basically there's a gas coming off the comet which is then activated by the sun, and it wobbles. We thought that's interesting. We could see the wobble on the electric measurements. We thought, why don't we speed those up and put them through a speaker and try and listen to what the comet's singing, or what it's trying to sing and tell us. And so this is what a comet sounds like from 500 million kilometres outside the asteroid belt. Now that is the sound of a comet, believe it or not. Obviously we can't hear it, it's in a hard vacuum, but electrically it's creating a signal which we can amplify and measure and convert into a sound. And you hear the frequencies going up and down, there's all sorts of weird things that are going on, we don't know what they are, we've got no idea what's creating this. But the Plasma Consortium scientists have gone berserk now, trying to figure out what on earth is this? Because it's a very, very interesting signal. The comet's extremely cold, it's extremely far from the sun, yet it's in fact very active. And this is a very much unexpected event. So then we started looking for a landing site. And this is the difficult bit. The comet is incredibly rough and extremely weird shape. And we had to try to get our lander, which is very fragile, onto an almost zero-G surface. And if we hit anything, it would tip over. Now, as you can see, I told you these are not boulders, they're chunks of frozen ice or some other volatile material, we don't know quite what it is yet. But this is the smoothest part we could find. And this was where we had to get as much sunlight as we could, and a flat surface, and also try to miss the boulders. Well, 50% of the best place we found was still unsuitable, but there was nothing else. And we'd carried the lander all this way, well, we had to put it down. So we decided this is where we were going to do the landing. So this is the landing sequence of what we wanted to have happen. So this is a video generated by ESA showing what we hoped was going to happen, I should say. So Rosetta is flying over the comet at about 18 centimetres per second, and the little lander on the back gets pushed off at exactly the same speed, so it's effectively stationary above the comet. So effectively stationary, and then we start drifting down about 1 metre per second from 22 kilometres high, and it took about 7 hours to get down. We open the landing gear, we open up the instruments and the antennas, and we start drifting down towards the surface. When we get down, we have 2 harpoons we want to fire and to hold into the comet surface. And there they are, the 2 red ones there, were meant to be the harpoons which we're going to fire. But they didn't. And I'll show you the consequence of that. Okay, so this is the real sequence. This is using our high-resolution science cameras to film Philae as it was going down onto the surface of the comet. In the background, in that white square, is a full field view of the comet. Can you see it? Again, I'm trying to emphasize how dark the surface of the comet is. Because the little lander was lit by the sun, we were interested in filming that. There's no way we could see the surface. It was so dark, to analyze that, we would have washed out the lander. So just again, trying to emphasize just how dark and how difficult it is to even see the comet. So this is us coming down with the camera underneath the lander as it's descending onto the surface, and this is part of the landing gear in the field of view of the camera. We're coming down, this is again 40 metres above the surface before our first touchdown, and everything was looking good. We got to within half a metre of where we were aiming from 22 kilometres away. This was an unprecedented result. People just couldn't believe how good this was. But unfortunately, of course, it was too good. We bounced off. We knew we hit the surface because those microphones on the feet of the lander, which I mentioned to you before, well, we heard them make the touchdown, and this is what we heard. Hello? That was it. That was a touchdown, okay? But it was a positive signal, and we knew we'd hit something, okay? Okay, so this is what we wanted. We wanted Philae on the nice flat surface in the open sun, analysing a nice flat surface. We expected every image, there are 6 cameras around the edge of the lander, and we expect half to be dark sky and half to be sunlit surface of comet. So sky at the top, land at the bottom. Well, this is what we got. So this is, or getting to that, sorry. We realised something had gone wrong when we were imaging the landing point, and all we could see was a puff of dust. So the green spot is where we were aiming, and this little light grey area here, this is the before and after of the touchdown. So this is before and after, and there was a dust cloud. Good news, we'd obviously hit somewhere close to where we wanted, but the lander wasn't there. So we thought, well, where is the lander? Well, then there's another image about the same time, and one of the flight dynamics people realised that in this image we could also see the little lander. This is from 22 kilometres above, looking down for a half-metre height sized box of electronics for the lander, and we could see 1 pixel, which was the actual lander and its shadow on the surface as it drifted away after it bounced off. And so this is an incredible image. To get this, again, I keep on emphasising how dark it is and how far away, but to get this kind of image is just unprecedented in space exploration history. So we realised that instead of landing here, which is the area we wanted, we'd landed over here in this very rough, very dark, craggy surface. And again, this is another image showing the descent of the Philae down to the surface, looking down from Rosetta. We can see a series of these 4 images here as we're coming in. This was the area we wanted to land. This is a before image, and the after, where we can see the 3 little footpads, which had left an impression, but no lander. At that same time, at 1543, we were looking around here to see, could we see the lander? And there it was, right over here on the right-hand side, in the dark. In fact, it was still drifting. We could see the little lander as it was about to leave the field of view of our camera looking down. So it did land eventually. After 1 hour and 50 minutes, it did actually stop bouncing around and it came down. And we started processing the 6 panoramic images, and this is what we saw. So this is camera number 1. It was extremely dark, and we realised, wow, this is really unexpected. We wanted to be in the nice sunny plain, but we could see a dark wall, and the top half was not dark space, and the bottom half was not nice sunlit land. It was something very strange. Camera number 2 was looking straight out into space. I thought, that's strange. How on earth can that happen? So dark space, this is one of the antennas of one of the instruments, so it was a valid image, but it was not seeing landscape. Then camera number 3, we could see some sunlit surface again, but again, on its side or something strange. Camera number 4, again sunlit, looking promising. 5, very dark. 6, very dark. So we thought, well, what is all this telling us? Well, we did some processing, and we put the best images together, 3 and 4, and we got this sort of looked like the wall of a cliff face, a wall of a crevice, sunlit, with the lander leg here in the foreground. Then we added the colour and put some depth of field cues in, and we realised that we really were caught in some kind of a crevice. And this, it's not a very good image, I'm sorry, but this little blue cube here, this is the actual lander with its legs tilted on its side. And we realised that we'd bounced into a small crevice and tipped over on our side. We could still do science. There was no problem. We managed to get a full set of measurements, which are still being processed. And we are now waiting for reactivation, which we think will be in July or August of this year, when the sun will be coming down onto one of these solar panels with enough sunlight, with enough strength to actually turn the lander back on again after the first 3 days of science, which we did when we first landed, using a non-rechargeable battery. We did a full suite of science in this position, and then we hope to do another phase when we get closer to the sun. So that's the end of the presentation, but I do, just to answer this one question, I get a lot of people that ask me, how on earth did I get to work on this project? Okay, so this is the most important question to answer. Be a very ordinary student, okay? But be committed, determined, and hardworking. I was a very ordinary student, but I really, really, really wanted to work in space. I saw Neil Armstrong walking down the ladder on the Apollo 11 when I was in grade 2 in Adelaide. I was 8 years old, and from that day I was crazy about space. But I was just really an ordinary student. But I knew I had to study science, technology, engineering, and mathematics subjects. And that's what Waikato now is focusing on. And you need to have a really good teacher. And I did have the best, I'm absolutely convinced, the best electrical engineering lecturer of all the people I've ever worked with in Europe. And that's Professor Jonathan Scott, down here. Okay, where does Professor Jonathan Scott work? I'm so glad I'm embarrassing you. And you have to get into a good university, and that's Waikato. So Professor Scott is working at Waikato University, and they have an emphasis on STEM subjects, and that's all you need. So if there's anybody here in this audience who's an average student and wants to do this kind of work, there's no excuse. It's all here for you. I want to thank these people who helped organise the talk, I have to do this for legal reasons. These are all the credits for all the images from the scientific institutes. And that's the end of my presentation.
Moments for some questions before we have to proceed out into the foyer. So if we could have some questions from the audience, please. Before you speak, if you could identify who you are and then proceed with your question.
Is there just one microphone? Or
Marvellous, marvellous, thank you. I wish I was 23 years old and just starting, and I'd do exactly what you said. The orbit of the Rosetta around the Comet, obvious very low gravity, very slow speed, everything happening very slowly. Is it a stable orbit, or is it requiring continuous orbital adjustments to maintain its position with relation to the asteroid?
What a fantastic question. You need to come and work with ESA. Okay? That is actually one of our biggest problems, was to know how close do we have to get to be able to close the orbit. We had no idea. We had no idea how heavy the comet was. We didn't know anything about the shape. The shape was a complete surprise. It turns out we had to get within 30 kilometres to close the orbit. We did a series of triangles coming in front of the comet. So the sun was over there, the comet's here, and we did a series of triangles like a pyramid. And we got slowly closer and smaller until they started to bend. And then they started to bend, we realised, well, there is a gravity on this thing. It's extremely small, 1/100,000th of a g. But as we got closer and closer, we got to 30 kilometres, we realised if we slow down to, what is it, I think it's 10 centimetres per second, we can close the orbit. And then we got down to 20, we got down to 10. I think at 10 kilometres above the orbit, it's something like 18 centimetres per second. It's ridiculously slow, about 1 kilometre an hour. But that was enough to do a circular orbit. And then we were around what we call the terminator. So the comet's turning underneath us, and we're 10 kilometres, and it's great for getting imagery too. So we've got these very powerful cameras, and we're scanning right down to centimetre size pieces of ice, not rocks. And so that's the big unknown. We had no idea how close we had to get before we could close the orbit. Luckily, it all turned out well. We were close enough without getting blown away by the gas and dust evaporating, because we got there before it was activated. So we've scanned it like crazy. Now we have to move up to about 200 kilometres away, because there's simply way too much dust, and it's blinding our star tracker. You know that star tracker image where I showed you couldn't see the stars? Well, we actually had a serious event about a week ago where it got blinded and we lost navigation for a few minutes. And we went into what we call the safe mode. First time it had ever happened. So we recovered from that and we realised we have to get further away. But luckily, we got science for 6 months, very close. We go further away during the active phase, and then we come back in again in July next year. Okay.
Hi. I was just wondering, is there any particular reason this comet was chosen versus any other in a comparable orbit?
Yeah, good question. The problem is catching a comet. All comets, by definition, are normally outside the orbit of Pluto. I mean, there's a place called the Kuiper Belt, which is outside of Pluto. And much further out, there's a sphere called the Oort cloud, which is 100,000 times further than the Earth to the Sun. 100,000 AU, they call it. There's a reservoir, a great big sphere of billions and billions and billions of comets, which are very far out. The only reason we can catch this one is because one of those comets got disturbed at some stage by a collision or an interaction, even with a passing star. The comet came in, went around the sun, but Jupiter was luckily in the right position to catch it. You need two bodies to catch a comet. One, it just comes in and goes straight back out to where it started. That's what we call a single focus. With a double focus body, you can catch the comet and you reduce the size of the orbit enormously. They're called Jupiter family comets. There's about 500 of them, but only 22 of them are actually close enough that we can catch with an Ariane 5, full power, and 10 years of gravity assist. So we had very limited options, and this was just turned out for a series of different reasons. Of those 22, that was the best one for us to catch.
When you land Rosetta on the comet, will that extra mass change the orbit of the comet in any way?
Oh, great question. Okay. Rosetta weighs 3 tonnes, fully fueled. 1.7 tonnes is fuel, which would be exhausted. So we're down to about 1.3 tonnes. Even though the comet is 4 by 3 by 2 kilometres, roughly, it's a very strange shape, it actually weighs 10 trillion tonnes. Okay, but that, believe it or not, is nothing in the mass of solar system bodies. I mean, what's the mass of the Earth? It's 10 with 31 zeros after it, in kilograms, okay? So it's incomparable in terms of the Earth, but it's still massive in terms of the comet. What you've got to understand is that the comet is evaporating hundreds of tons of material every time we go past the sun. So about 5 to 20 metres of the outer layer of 67P will disappear in this, what we call perihelion passage. It's a 6.5-year orbit. When we come back in again, we're going to lose another 20 metres. I forget how many tonnes. I've calculated how many tonnes that is, but it's several thousands of tonnes. The comet's going to be around forever because even though it's evaporating and the volatile material is coming off, there's refractory material which doesn't evaporate, and that's like Murchison meteorite, which is like a black rock. Well, that will be left over one day too. As all the non-volatile stuff compresses into form a rock, there will be just a rocky, inert core left, and all the volatile stuff is gone. But in terms of mass ratio, it's almost insignificant, and whatever we add is going to be evaporated off the next time anyway. So.
Could you talk a little bit more about the internal structure? You've got your goosebumps about 3 meters across, I understand. Are they a bit like chondrites in meteorites? And do they predate the banding? What's the sequence of events, do you think?
Well, that's what we don't know. I mean, we've seen for the first time ever evidence of the internal structure. So we've got this feature, which is a well, and we can see on the wall of the well there are golf ball size. They're golf ball size. They're not chondrites about the size of grains of rice. Chondrites from meteorites, chondritic meteorites, have also undergone heating, and the comet hasn't undergone heating. By definition, it's a primordial frozen body. So it's a different chemistry, a different formation process. We thought there were little golf balls that made the goosebumps, but then we also saw layering. So when the comet was first being made, 4.5 billion years ago and more, it was flying through these huge clouds of dust, which was slowly collapsing under gravity into a big disk. They call it the accretion disk. And we were flying through clouds of dust of elements and strange carbon chemistry and forming layers. So there is sort of this onion layer process to make the comet originally, billions of years ago. Where the little golf ball goosebumps come from, nobody knows. It is actually a theory. There's something to do with the electrostatic charge of dust over a certain distance, blah, 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 blah. I don't know what that is. But both theories seem to be correct. So there were golf balls drifting around there and layers of gas clouds. They both seem to have been responsible for making the structure, but they're not chondritic little chondrules from meteorites.
Thank you sincerely.
That's right.
Because there's different chemistries, do you all ever consider that the mass signatures that you're looking at in the mass spectroscopy might not be silicon or CO or nitrogen? Because you can see different amino acids that we wouldn't have here otherwise, that these are something completely new?
Right, great question. Okay, that's good. We are still limited to the fundamentals of elements. Okay, so we have the same elements and we're assuming the same isotopes, because in everything we've ever seen and all of our interplanetary science, the elements are the same and the isotope ratios are not necessarily the same. They're different for different reasons, but they're the same isotopes. We might get more exotic isotopes naturally occurring we haven't seen on Earth or maybe on some other planets. But in the lab, we know what isotopes exist and we know what to look for. So outside of any unknown isotopes, I don't think we're going to see anything unusual. We'll certainly see strange combinations, and we're seeing that right now. As far as the amino acids are concerned, yes, we're seeing certainly amino acids which do not exist on Earth. And theoretically, I think there's something like 500 potential amino acids you can make just with the definition of what an amino acid is. What is really unusual, and I didn't say this because I was limited for time, is we have seen the big unusual thing with life is all the biogenic carbon chemistry that makes us is based on a chirality of carbon chemistry. We'll go left-handed or right-handed chemistry, not left-handed humans, but left-handed shaped molecules with the same elements as right-handed shaped molecules. So we've got the left and a hand, and we've both got 4 fingers on each hand, but the thumbs are on different sides. Okay? Human life is based on left-handed shaped molecules of chiral chemistry. Why left? When the processes on Earth that form amino acids actually create the Miller-Urey experiment, made equal numbers of left and right-handed. That doesn't explain where human life started. We looked on Murchison, we found an 18% excess of left-handed chiral chemistry amino acids. So we're looking now to see if we can find again left-handed amino acids, and that explains that the bombardment of comets on the Earth not only brought water, not only brought amino acids, but brought left-handed amino acids. I mean, it's all too incredible for words. You and I are made from a comet. This is what we're going to prove. Yes?
Hi there, Mark from Kiwi Space. Just a question, at the end of the mission, when you spiral Rosetta down and touch down again, are you anticipating still being able to continue science at that point?
Well, I think we can. We're going to be very limited because, Rosetta was never designed to go onto the surface of the comet. It's actually got by far the best mass spectrometer, and the best instruments are actually on Rosetta. We'll be turning the solar panels so they will be facing out. We do know they'll be rotating every 12 hours. So we're expecting to get sunlight, a lot of sunlight, onto the lander when we first come down on it. Now, as we go out, we're going to have the same problems why we had to go into hibernation. And that is, we are just going to one day get too far away that even the big solar panels of Rosetta won't have enough power. But I'm certain that in those first few months after we've come onto the surface, that we will be able to do science with those instruments on Rosetta, for sure. Poor old lander will have been long dead because it's in a crevice and it's hidden away. We will be able to bring down Rosetta anywhere we want. The navigation of that big orbiter is just incredible. We can get to within millimetres with where we want to get with that. We can bring it down. We've got 24 thrusters to bring it down incredibly slowly. We can do the softest landing you can imagine. In a sense, the lander would have been a better lander than, sorry, the orbiter would have been a better lander than the lander. But it will get down, and we're almost certain that it will stay down. Now, whether or not we can get meaningful science out of those instruments, we don't really know. They haven't actually wasted time planning that yet. We're still busy doing all the science we can in orbit, but they will certainly plan and do some incredible things. This is what I love about ESA, is they can do the most incredible things when you don't expect it. Even getting to this thing was incredible. First time ever in the history of man, of humanity, that they've got to a comet on the first attempt, orbited and landed. There have been 51 missions to Mars. Starting in 1960 with the Russians, only 42% of them have succeeded. Now, Mars is a huge planet, a huge gravity. It's got an atmosphere to slow down in, to do a landing. We know the orbit of Mars better than the back of our hand. This comet has been past the sun 8 times, and we can barely see the thing, as I keep telling you. To go into orbit around that and land on it with a body with no gravity, completely black, with no atmosphere, I still can't believe it. I mean, I'm just waiting for all the conspiracy theories that the whole thing was done in Hollywood.
Hello, Warwick. I'm Brian.
Sorry, where are you, Brian? There you are. Hello.
I hear that you mentioned that New Zealand should join the European Space Agency, and I wondered if it is a club that we could join. I noticed that you mentioned that project is $2 billion over 11 years, a little over 200 million a year. Mm-hmm. If we did join, what would that cost New Zealand?
Well, that's another really good question. I really use that argument for trying to make Australia join, because I'm Australian, but it does apply to New Zealand as well. You can become an associate member of ESA very easily. Canada is an associate member of ESA and has been for 40 years. The formula for joining ESA is, I think, it's about 0.05% of the GDP of any European or associate country is what the contribution is. They calculate it for different reasons, but that's about the figure, which means I think in New Zealand terms it's about $8 to $10 million a year. New Zealand could be an associate member of ESA and do missions like this. Now, the way it works is that if you become an associate or member of ESA, you get what they call geographic return, and they guarantee that every dollar you put in, you will get that dollar spent back in your country in some industry somewhere here in New Zealand. The Canadians have been looking at this very carefully to think, well, is it really, why are we members of ESA? Why is Canada an associate member of ESA when they've got NASA right next door? It turns out that for every dollar they invest, 3 different universities have calculated they get $3.50 back in profit. And that means that ESA gives you money. you gain profit when you join ESA in terms of technology and in terms of selling high-tech with those companies which then are spin-offs, I guess you could say. And so for Australia, it's about 15 million a year, which is really nothing when we spend, Australia, 30 billion in our defence budget. We paid for the entire 25-year Rosetta mission in 3 weeks in our military budget in Australia. $2 billion in 3 weeks is it 25 years, and look at the results we got. So it's just a bit frustrating because I've had to work for 29 years away from Australia doing this work to do it. And for me, the question is why? Australia is one of the members of the OECD, 35 countries, and we're the only country that doesn't have a space agency. Even Vietnam has a space agency. They build their own spacecraft. I'm not meaning in a patronising sense, but why is Australia doesn't it have its own federally mandated space agency? And I don't think New Zealand does either, I'm not too sure.
Thank you.
Hi. How long will the lander stay on the comet? Will it be a human landmark like the moon lander, or will it get shot off?
I'm sorry, I couldn't hear that.
How long will the lander remain on the comet? Will it be a human landmark like the moon lander, or will it get shot off?
The markings on where the touchdown was, they will certainly evaporate away at some stage. But as I said, as the volatile components of the comet evaporate after millions of years of going past the sun, the non-volatile parts of the comet, the metals and some of the refractory molecules, will mean that there's a rock, basically, a gooey black rock will be left over, and the orbiter and the lander will still be stuck on that rock, because the gas pressure, even evaporating right underneath the lander, is nowhere near enough to blow it off. We need an escape velocity of 1 metre per second to leave the surface of the comet. And there's no way that the pressure of an evaporating molecules underneath the lander can do that. So we are definitely on the surface for the rest of the life of the comet, or of the solar system, I guess. And there'll be remnants of human exploration for the rest of the life of the solar system.
I think we have time for one last question.
Yes? Is there a mic?
Hi. So one of the benefits of space exploration is the kind of collateral benefit, like you develop new technologies which can be used in all sorts of other places. So what would you say the biggest breakthrough that came from this mission was?
Good question. It's difficult to look at these scientific missions and say directly, because we measured an amino acid on a comet 500 million kilometres away, what direct effect does that have? Well, one of the effects you could say is we've made mass spectrometers which can fit into a shoebox, and they can be sent to Africa. You know, mass spectrometry used to be something that filled a room. Okay, well, we were determined to get something the size of a shoebox to land on the comet. So that technology was, you know, for benefit of mankind. It's a bit indirect, but definitely we have miniaturized mass spectrometry, gas chromatography. But ESA have got just books and books and books of the benefits from, you know, GPS. People thought, well, when we first put our first atomic clocks into space, we wanted to measure the Einstein effect, and that was the change in the frequency as we went through a gravitational field. People think, well, why are you doing that? What a ridiculously stupid thing to do. Well, today we have GPS, and that's a constellation of 32 atomic clocks used to tell you where you are in your car. And does anybody think GPS is worth it? Okay, so with all of these benefits, anything to do in space with remote sensing, looking at the huge storm that hit Sydney, well, I've been away, thank God, we could see that thing coming for miles, you know, and everybody could button down and get ready. Well, that's again because of remote sensing, looking down. So when we put our first cameras in space, people thought, why are you doing that? Why do you want to take, you know, we know what clouds look like. Well, look what we can do today. With infrared spectroscopy, we can look at the velocity of the clouds and where they're coming from in 3 dimensions, right through the clouds. So at the beginning, it doesn't seem obvious. You know, what are we doing this for? But later on, incredible things come out. And that's the best answer I can give. But I guarantee you, out of Rosetta, there'll be some huge benefit for humanity.
Right, I'm going to call the proceedings to an end right now, but before that, before we go out to the foyer, for those of you who wish to ask Jonathan which courses they can enrol on next year, and those who wish to ask Warwick if there's a job available as well in Europe, I'd like to thank you. There's some gifts from the university. Thank you very much.
Thank you very much.
I'm hoping it's our subscription to the Space Agency.
Yes, so am I.
And please join me in a round of applause. Thank you very much.
Thank you very much.
And hopefully we will continue our conversations outside in the foyer. Thank you.